Hi everyone. Today I'm going to give a talk about the work I did together with my advisor and a colleague at the Technion. The work is about GoSeed generating an optimal seeding plan for deduplicated storage. Okay, so let's break it down. What is seeding? Seeding is just like the data migration problem that we all familiar with, but with slight change. The difference here is that the destination volume is initially empty. Okay, so in the data migration problem, when we move files and their associated blocks to the destination volume, there were many studies on how to do migration efficient in terms of times and resources. Today, we'll see how we pick correctly the files for the migration in order to make it efficient. So in the duplicated storage, what happens is that we save only a single copy of each physical block. And then what happens is that a certain block can be associated with more than a single file. So thus, if we remap a file to our destination volume, we cannot necessarily move all of these files associated blocks because some of them may be still needed in the original volume. So in order to solve this, we replicate this data block and save it on both volumes. And our goal in this work is to write a smart seeding plan such that we minimize the block replication. Just like before, data migration is important because of load balancing, and even the simple case of seeding is interesting because let's say we have some on-premise storage system and we have a cloud tier and we want to clear some space on the on-premise storage. So picking the right files can be very essential in order to get good results. Okay, so in our optimization problem, we aim to migrate ampersand of physical occupancy from our source volume into the destination volume. And to minimize the block replication that we saw, which is a side effect of the duplicated storage. And each file is going to be either kept or remapped. And each block is going to be kept or moved or replicated. All right. So in our approach, we take this very interesting problem and we transfer it to another a classic computer science problem, the integer linear programming problem. And we take advantage of its popularity that led to development of industrial and open source solvers to the problem. So we're going to take advantage of them in order to give a very good, fine solution. So the agenda here is that we first start with our seeding problem, and then we formulate our integer linear programming problem, which is going to be the input to the solver. And after we retrieve the solution from the solver, we're going to apply the seeding plan into our system. Okay. Okay, so we've talked about what we want to minimize, and now let's talk about the constraints of the problem. So first I can promise you that we're not going to talk about any equations. And the first constraint is going to just to migrate ampersand of physical occupancy from the original volume into the empty destination volume. Actually, we're going to allow a tolerance of epsilon, so any occupancy between n minus epsilon to m plus epsilon is fine, because, and we believe that the system administrator does not necessarily care if it migrates, let's say, 30% or 30.5% of the system, or 21.7. Yeah, okay. And the second group of constraints is that if a block, is that because we're not in a distributed storage system, so we assume that each block should rely in the storage volume of its files. And so if we remap a file from our source to the destination volume, the destination must include all of the files block in order to retrieve the file information. And at this point, we don't care whether if these blocks are moved or replicated. As long as they are there, it's fine. All right. Okay, and the last group of constraint is that if a block was moved to the destination volume due to some, let's say, some other file it belongs to, and then all of the associated files that includes this particular block will also have to be remapped into the destination volume in order to preserve the integrity of the data. Okay, so far we talked about theory only, and you guys know what's the difference between theory and practice. Well, in theory there's no such difference, but in practice we're actually dealing with huge systems, and the scale is very big. So just 10 logical terabytes of data can lead up to billions of variables and constraints in our integer linear programming problem. And the known solvers that we're taking advantage of are efficient with just several hundreds of thousands variables and constraints. So there's a gap to bridge, and the way we do it is that we suggest the concept of acceleration methods. In acceleration methods, we aim to reduce the time taken for the solver in order to output a solution. But because everything in life is a trade-off, we are going to lose the optimality, the theoretical optimality of our approach. And this is because we want to give practical solutions in a reasonable amount of time. Okay, so the first method we suggest, the first acceleration method we suggest is solver timeout. And solver timeout, we're using the solver's ability to halt the execution and output the best solution found so far. And this is okay because we're in a systems problem, and we don't necessarily need the theoretically optimal solution. Another good thing is that, fortunately, from our evaluation, we learned that most of the progress that made by the solver is done early. So we are not going to lose much. Okay. More of these can be also shown in the paper, seen in the paper. Okay. The second acceleration method we talk in the paper is the fingerprint sampling. And in fingerprint sampling, we sample only a very small fraction of the blocks in the system, and then we formulate our integer linear programming according to it, and using the solver in order to solve a smaller problem. And after we retrieve the solution, we conclude about the larger system. We define a sampling degree of k as sampling just half to the k of the system's blocks. And with tuning the parameter k, we can achieve a smaller problem that will reduce the time taken to the solver to output the solution. But on the other hand, we are going to probably lose more information. So we need to be carefully with this. Okay. Last but not least, acceleration method is container-based aggregation. Here we know that a commercial deduplicated system use containers in order to store their information, such that each container contains thousands of blocks, and we're going to treat each container as a block. So or we're moving the whole container, or we move none of it. We're not going to break the container into the blocks. And thus we're going to have a much smaller problem, because there are much more blocks than containers. And another good thing is that we don't need to decompress and unpack the containers during the seeding plan. So we don't lose time and resources on this. The way we treat each container is that we're going to have an association between file and container if at least one of the files blocks includes if at least one of the containers blocks, includes in the certain file. So we will create some. This creates some false dependencies. We can see that file 1 and file 3 do not share any block, but they actually share a container. Okay, so okay, so before we move on to our results, let's talk about the experimental setup. So we compare our approach, GoSeed, to state-of-the-art greedy algorithms for the same problem. The first one is called Rangoli, which basically sorts and divides the blocks into bins and then choose the cheapest bin for the migration. The other one is sgreedy, which is a iterative method, and that each iteration we pick the best file for the transfer. We evaluated our results on several workloads. Now due to the time restrictions, we'll look only at 3. And the thing that we want to look at is that the main difference between the workloads is the duplication ratio. Okay, so the first thing the first comparison we're going to look at is the cost comparison. Here we have on the x-axis M, the parameter of the physical occupancy we want to choose for the migration. On y-axis, we have the cost, the percentage of blocks replicated due to the seeding plan. And on our first workload, which had a low deduplication, we can see that pretty much all the algorithms came up with a solution, and the solutions were relatively low in cost, and which is good, but still we can see some differences between the algorithms, where GoSeed, which is our approach, is the best cost among all, or very close to the best. The second workload we're going to we see which had a higher deduplication. We can see that some missing bars, and these missing bars indicate that some of the algorithms did not come up with a solution to this problem on these certain parameters. But what we can see is that GoSeed always came up with a solution, and most of the time it was the best solution in cost among all. Okay. on our last workload, which had a very high deduplication, and this is due to its characteristics. This workload is made out of 200 daily backups, which were taken consecutively. And here we can see that all the algorithms, or some of them did not come up with result, and those who did came up with a result which had a very high replication cost, and this is due to the hardness of this workload, which is deduplication intensive. But we can see that overall GoSeed always come up with a solution which is often the best among all the rest of the algorithm in the terms of cost. Okay, the second thing we're going to look at is the time taken to the solver in order to solve the problem. So here we have same x-axis, same algorithms, same everything, but only y-axis is changed. Now it's going to show a time in seconds, and note that it's in log scale, so lower is better. And here we can see that two things. The first thing is that sampling our acceleration method of fingerprint sampling actually works well it reduces the time. We can look at the blue bar, which is as greedy with no sampling, and we can look at the lighter blue, which is as greedy with sampling degree of 12, and we can see there are much difference by some orders of magnitudes. The second thing we can see is that GoSeed actually don't find GoSeed time in order to find the solution is relatively high, and this is because we're trying to solve a NP-hard problem, and this takes time. But the good thing is that most of the time it's just a matter of minutes, and the rest of the time we can see that always GoSeed finds a solution where the other algorithms do not necessarily did find. Okay, and the last comparison we're going to look at is the container comparison when we perform our seeding plan in the granularity of containers, which was the third acceleration method I presented. Here we're going again to look at the cost, and here we can see that GoSeed always finds a solution, and almost always it's better than other algorithms. Additional evaluation of some other parameters like m, like epsilon, the tolerance, timeout parameter also, and the parameter of k, which is sampling degree. Everything is evaluated in the paper. Okay, so to conclude, we took a very interesting problem in systems, and we transferred it to a very classic problem in computer science, which both problems are NP hard, but the second one is a little bit more popular by for some years, and due to its popularity, we took advantage of the fact that there's a variety of the developments of solvers in order to solve this problem. But still, there's a gap between what these solvers can do in a reasonable amount of time and what we actually want to, the scale of the systems we're dealing with. So in order to bridge this gap, we presented the concept of acceleration method. We gave 3 examples, which will, the acceleration method reduce the time taken for the solver in order to solve the problem, but we lose the theoretically optimal problem. But it's fine because it's just a systems problem. And we evaluated everything on real workloads, compared it to current state-of-the-art algorithms for this problem. We saw that GoSeed often outperforms the greedy algorithms in their cost. Okay, so we looked at the seeding problem, which is the simple case of the data migration problem, when we have multiple storage volumes, multiple source volumes, multiple destination volumes, and we want to perform load balancing between them. So, but we still think that this approach can be also applied to the general data migration problem, but we're expecting some challenges due to the scale of the problem. All right, thank you.
Keith?
Hi, Keith Smith, MongoDB. So fun paper. I like seeing somebody looking at a deduplication problem that we haven't seen so much before. I'm curious whether you've looked at the actual plans that GoSeed generates and compared them to the other methods. Are there any patterns or things we can learn from what GoSeed finds that would let us design a better heuristic and avoid the overhead of actually running an ILP solver?
Yeah, we actually looked at like the current, like the concrete files that GoSeed choose for the migration and the other algorithms, what they choose, and we saw that on a very small migration parameter, the M parameter, these files, some of them are the same, but when we enlarge the parameter of M, we can see more differences in the files they choose, and this is we thought that this is one of the characterisms of greedy algorithms, that on the low scale they are fine. Yeah, that's why. Thank you.
Okay, thanks for the interesting talk. And this is Zhichao from Facebook. So I have one question. I read the paper, and you see you use the sampling method that follows the method from the paper in 2019, last year, right?
Can you repeat this?
So I mean, you do the sampling for the chunks in the container, and the sampling method is from the paper last year.
Yeah.
And have you thought about using other sampling methods, for example, change different sampling points and make the sampling ratio adaptive to different containers based on the hints from different files and workloads? Okay,
so I think that if I got you right, what you're asking is that if we checked out some other sampling methods, because the one that we checked was, can you maybe explain some more?
For example, you can change the sampling ratio in different containers based on some of the pattern.
Oh, we don't sample containers. We sample according to the hash value of each block.
Okay, but I mean you can change the sampling ratio, right? You can change the sampling ratio
you can
to
tune the
reduce
parameter
the
K.
overhead of the calculation.
You can tune the parameter K.
Okay, have you thought about that direction?
Again?
So I mean, have you thought about that direction to do the tuning on the sampling ratio and the method?
I'm not sure I understand.
Sounds like a good lunchtime conversation.
Okay, sure. Thank you.
We should find each other for lunch. Bill, do you still have a question? Or you?
Bill Jannon, Williams College. If in addition to caring about how much data I migrate, I also care about which files get moved, is that much harder to add as a constraint?
Yeah, you actually can restrict some files in the integer linear programming problem, and tell the solver, I want this file to be migrated no matter what solution you're picking.
Thank you.
Yeah.
All right. Well, I know better than to stand between people and lunch. So let's thank our speaker one more time.